Hello and welcome to the bear pit. Why do I call it a bear pit? Explaining the phenomenon of lift seems to be one of those subjects that excites great passions. In addition to the standard aerodynamic text, there are whole books devoted to the subject of explaining lift in non-mathematical terms. On aerodynamics discussion groups, there is often a continuous active thread devoted to the subject. The arguments get very heated. The thing about lift is that it's by no means intuitive that it should exist at all, and it's such a powerful force, often 50 or more times the drag. We can predict the lift using fairly simple physics to a very high degree of accuracy, but does that mean we really understand it? I've recently been helping out a bit at a local school. We are doing some work on flight. I was forced to think about simple explanations for lift, suitable for grade 9 students. Also, my lectures on aerodynamics for pilots generated some discussion on the subject. Lift is a complex phenomenon, so there are many equivalent ways of thinking about the same thing, making for endless arguments. In this lecture, I will explain how aerodynamicists get their incredibly accurate predictions of lift and drag, and try and boil it down to simple one-paragraph explanations. Here we have a very standard explanation of lift. This is the explanation given in the children's area of the Smithsonian Aerospace Museum, for instance. We start with something that looks a bit like an airfoil, and now we add another upside-down airfoil to create something like a two-dimensional venturi. We blow air through the venturi, and lo and behold, we have low-speed flow at the mouth of the venturi and high-speed flow at the throat. And now Bernoulli is introduced as a kind of magic trick. His principle is presented as a discovery without explanation. It just is. Now we take the system apart a bit. We take away half the diagram. The idea is that the flow remains identical when half the venturi is removed, so the suction, if you like, at the throat remains and causes lift. There are several problems with this explanation, including the fact that the half venturi doesn't have anything like the same flow pattern as a full venturi. But more importantly, how can a symmetrical airfoil produce lift? And even more difficult, how can an aircraft possibly fly upside down? So that is not a particularly convincing explanation, is it? There is another explanation given for lift, and that is the longer path explanation. Looking at this picture, you can see that the air flowing over the top of the wing has to flow from a bit underneath, round the nose of the aerofoil, and then backwards to the trailing edge. In this example, the top path is about 10% longer than the bottom path. By the way, note that this is actually a symmetrical airfoil. The air flowing around the airfoil must meet up at the trailing edge, or eventually you're going to get a vacuum somewhere. So the idea is that the flow on top of the wing has to be faster than on the bottom, and hence, by Bernoulli again, you get low pressure on top, which creates lift. Now, of course, this is all absolutely perfectly true. The longer path is caused by the position of the front stagnation point. But it's not very obvious as to why the front stagnation point has to be there. In fact, it is where it is just because that's the way that flow continuity works. There's no other way of explaining it. So we have another answer in this case. It's true, but it's irrelevant. Firstly, a 10% increase in average flow doesn't seem very much, and it isn't. In fact, if you assume the increase in velocity of it is a uniform 10% over the whole top section, it accounts for only about 1/5 of the actual lift that you get. The reason is that the pressure drop depends on v squared, so the average velocity is a very poor measure of anything. The true answer lies in the detailed velocity distribution. For instance, the velocity near the nose is almost twice the free stream velocity, and most of the lift occurs there. In fact, you don't actually need a longer path at all to come up with a velocity distribution that will cause lift. All you need is to have a lumpier distribution on the top than on the bottom. So the longer path explanation is true, but not useful. So how do we get to understand this phenomenon then? Let's start by looking at the full picture from an engineering viewpoint. First, we need to get some basic principles understood. The first one is the conservation of matter. What goes in, comes out. Fairly intuitive. A streamline is defined as a line parallel to the flow at that point. You can think of it as the wall of a frictionless pipe. So if the streamlines are diverging, then the flow has to be slowing down, simply because the same mass has to flow at the thick end as at the thin end. And because the effects of compressibility are negligible at low Mach numbers, there's a conservation of volume as well. This is a very simple concept, but very powerful. The second rule is that you can choose whatever frame of reference you like, as long as it's not accelerating. This is called the principle of relativity, and it had been found to be universally true by Galileo and Newton, amongst others. It was the extension of relativity to electromagnetic phenomena that gave rise to Einstein's theory of the universe. In our context, we can choose to look at a stationary wing with air blowing past it, or a moving wing passing through the still air, and know that the physics of the two systems is exactly the same. As an example of choice of frames of reference, let's take a glider circling at a constant bank angle in a wind. If you're so unfortunate as to choose to analyze the system relative to the stationary ground, you're faced with a very complicated looping motion by the glider, which constantly changes speed. At times the glider may become stationary or even go backwards if the wind is fast enough, only to turn and accelerate rapidly downwind until it turns again. If you choose your frame of reference so that it moves along with the wind, then the glider is doing perfect circles at constant g-force, and the problem is very simple. The answers you will get in either case are identical, but the complexity of the analysis is not. So we shouldn't get sidetracked by the still or moving wing question. Galileo has never been yet found wanting. Up to now, we have not really touched on what would normally be considered physics. The physics of flight are for the most part very simple. All you need is Newton's third law, force equals mass times acceleration. Another completely identical way of describing Newton's third law is that energy is conserved. The expression for energy conservation is called Bernoulli's principle. Bernoulli is nothing more than energy conservation, which in turn is nothing more than the force equals mass times acceleration principle. Now, Bernoulli, as we use it, is not exact. For instance, there is a height term that we ignore because its effect is very tiny. And then Bernoulli only works where energy is not dissipated as heat. Fortunately, that applies to almost the whole of the flow field, and the places where it doesn't work are well defined. So now let's have a look at a real wing. We have the flow directly over the wing, of course, and then we have some spanwise flow out towards the tips from underneath the wing and in towards the root on top, giving rise to the formation of vortices near the wingtip, which creates a trailing vortex and a downdraft, which is the ultimate cause of lift. There is a lot going on. So how do engineers deal with this? they first analyze the two-dimensional properties of the airfoil section. And then they use that information, plus inputs from the wing plan and the twist, to analyze the span-wise behavior. The results are answers which are very good engineering approximations of the real world for most conventional subsonic aircraft. So, how does the two-dimensional analysis work? We start with a two-dimensional model that depends only on continuity. If you place a two-dimensional airfoil in a simulated two-dimensional flow field, then mass and volume conservation allows for only one solution. That solution is a network of streamlines flowing in a frictionless way around the airfoil. Mapping the potential flow field is very complicated computationally because a change anywhere affects the whole flow field. It really took the advent of computers to be able to exploit potential flow analysis properly. And when you do it, what do you get? You get an answer which is completely ridiculous. What you get is a flow that has a front stagnation point that is underneath the airfoil. That's not so much the problem as the rear stagnation point, which is in the middle of the upper surface. This mathematical construct has the air flowing underneath the wing, having to make a sharp turn round the trailing edge and flow backwards up to the upper surface until it leaves near the rear stagnation point. Incidentally, this solution also has zero lift. Now, that's just kind of contrary to what we see and what we know must happen. We know that the flow cannot negotiate that very sharp turn. When we talk about the boundary layer, we'll see that boundary layers become unstable when the flow is into rising pressure. The pressure near the trailing edge is very low because of that very small radius of the streamlines around that sharp trailing edge. And the pressure on the back part of the wing is much higher. We know that the real solution has to have the flow leaving the airfoil at the trailing edge. So what we do is we add another flow to the system. It's perfectly legal to add flows together, and the one that makes everything work is a circulatory flow that's just strong enough to wash the rear stagnation point backwards to the trailing edge, where we know it has to be. Now the potential flow looks a lot like we know the flow around an airfoil to look like. And as a bonus, adding the circulation causes the wing to experience a lifting force. So here again is an example of potential flow around a symmetrical airfoil at an angle of attack of about 10 degrees. It has a lift coefficient of about 1. Note that there is no real physics so far. All we've done is use simple mass and volume continuity. But now that we've solved the flow field, we can draw the streamlines anywhere. And once we know what the streamlines look like, we can calculate the velocity anywhere. And our good friend Bernoulli gives us the pressure anywhere. And once you've got the pressure, you've got the lift. So the first question, the answers from the engineers is, does it work? And the answer is close but no cigar. The pressure distribution works very well near the leading edge, and it doesn't work quite so well near the trailing edge. And of course, the solution has zero drag, which would be great if it was true, but it's unrealistic. And the reason why we have discrepancies is that there is indeed an area where Bernoulli does not work, and viscosity is important, and that region is called the boundary layer. Now, air is not very viscous, But if there's any viscosity at all, then the flow speed on the surface of the airfoil just has to be zero. There has to be some kind of velocity gradient between that zero speed on the surface and the free stream velocity far away from the airfoil. It turns out that this layer of friction and turbulence is quite thin where the streamlines are converging, which in turn means that velocity is increasing, and which therefore means pressure is dropping. So when the pressure is dropping, you get a nice thin, stable boundary layer. Where the pressure is increasing, the boundary layer thickens rapidly, and you even get some reverse flow close to the airfoil. If the pressure is increasing too fast, then the whole flow breaks away, so that you no longer really have a thin boundary layer, but a huge area of turbulence. When that happens on an airfoil, we call it a stall. But for moderate angles of attack, the flow behaves reasonably, although the boundary layer does get thicker towards the trailing edge on the top. Now, boundary layer theory, plus the results of numerous experiments, allows us to predict boundary layer behavior quite accurately for different surface roughness and pressure conditions. So, as we know the pressures everywhere, we can predict the boundary layer behavior quite well. And so the wing behaves as in the potential flow field as if it was this new shape, not just the wing, but the shape of the wing plus the boundary layer. And now we can redo the potential flow, in this case, with the new shape of the wing plus boundary layer. And we may have to cycle through the whole process again before we get a stable solution. But now the solution that we get is really very good. When this solution, when it's compared to real experimental data, is well within engineering tolerances, both for lift and profile drag. The profile drag is obtained from calculating the loss of energy in the boundary layer. So now we can use the two-dimensional airfoil characteristics that we have calculated as an input to another potential flow field to calculate the spanwise distribution of lift and the strength and position of the wingtip vortices and the induced drag. And that is a completely frictionless potential flow calculation. So here is an engineering solution that works a lot better than in other disciplines, but it is not perfect. Only good enough, like all engineering solutions. Here are some of the solutions, some of the assumptions that we've made. Viscous effects are negligible, energy changes due to height are small, the temperature is constant, flow is steady, air is incompressible, the spanwise flow doesn't matter, the wing is rigid and doesn't distort, and you can probably think of a few more. So, has that answered the question of where lift comes from? Yes, I suppose so, in that the problem is understood well enough to make accurate predictions. But what do I tell the kids in grade 9 or 10, or pilots doing their licensing exams? So what in fact do I tell my kids? I start by saying that when the air flows past a wing, you can't just have a block of dead air left behind. The boundary between that block of dead air and the moving air could never be stable. It would always mix and so on. You can get a stable solution where you get separated flow with a tumble of swirls of air behind it. And that does happen on a wing, and it's called a stall. A stalled wing has very little lift and lots of drag. It happens when the wing is at too great an angle, more than about 15 degrees. Or if the flow wing is at a fairly low angle to the oncoming air, below about 15 degrees, then the flow can stick to the back of the airfoil and leave it smoothly from the trailing edge. This is what happens when the angle of the wing is less than about 15 degrees. The air bends itself down and sucks itself onto the top wing surface. The sucking down of the air sucks the wing up, causing lift. The tendency of air to flow to follow a curve is called the Coanda effect, but I don't expect them to remember that. I show them a practical example by blowing over the top of a piece of paper and noting that the paper rises into the airstream rather than being blown down. Now, I'm not very happy with this explanation at all. I'm not absolutely sure if a complete one-paragraph explanation even exists. If anyone has a better simple explanation, I would love to have it. All we can hope to be is to be truthful, even though we can't help being incomplete. So this is where I'll leave you. Thank you so much for your attention. I hope you found this interesting, and let the arguments flow.